Hi everyone, and this is Sandeep and you are watching SAMYANS Academy, and in this session we are going to discuss about metals and non-metals from class 10. Let us start now. Right. Elements are mainly classified into two types, metals and non-metal. Then how we can differentiate these metals and non-metals? By using their physical properties. By using their physical properties we can differentiate metals properties and non-metal properties. By looking at physical properties we can easily identify which one is metal and which one is non-metal. Right. Now yeah, in physical properties, first we have to discuss about the metallic luster. The shining property of the shining property of metals we called as the metallic luster. And to perform this activity, so you take some samples of iron, copper, aluminum, and magnesium, and clean their surfaces by rubbing with the sandpaper. Then the surface becomes shining, and this shining property we called as metallic luster. And the hardness. Okay, to perform this activity, just you take the knife and take some samples of iron and copper like that, aluminum and sodium and potassium. You cut with the knives. So most of the metals are we cannot cut with the knife. Okay, and some of the metals we can cut with the knife, and that metals we called as a soft metals. Example for the soft metals are sodium, potassium, and all first year group elements are the soft metals, right? Remaining all other metals are hard metals, and these metals we cannot cut with the knife. Metals are generally hard and cannot be cut with a knife. The hardness varies from metal to metal, but sodium metal is soft and can be cut with a knife. Okay, now malleability. The metals are can be beaten into thin sheets is called as malleability. So if you hammer this lump of the gold, and it can be converted into a sheet, and that property we called as a malleability. And gold and silver are the most malleable metals. Next one we have the ductility. Metals can be drawn into thin wires, and this property we called as ductility. And gold is the most ductile metal, and when you take the 1 gram of the gold, and this 1 gram of gold we can be drawn into a 2 kilometers of the wire, thin wire. Okay, that property is called as ductility. And due to malleability and ductility, metals can form the different shapes. Okay, by that property we can convert all metals into different designs, right? Now conduction of heat. So for perform this activity, what we are doing, we are taking one aluminum clamp and aluminum metal. Just you clamp this aluminum metal on stand, and just you heat on one end, and this heat is transferred to the other end. Then how do you check the heat is transferred to other end or not? For that, what we are doing, just you fix a pin with wax. When heat is transferred from one place to another place, this wax get melted and the pin get dropped. So this indicates that the heat is transferred from one place to another place. Is it clear? And this indicates that it shows the metals are good conductors of heat, and also metals are having high melting point. Then how do you know? Because of the heat, the wax get melted, but that aluminum metal does not get melt. So by using this activity we can we can know that metals are good conductors of heat, and also they have the high melting point. When you take the silver and copper are the best conductors of the heat, lead and mercury are the poor conductors of the heat. So what is the exception case here? Lead and mercury are poor conductors of heat. Next one, conductor of electricity. To know this, to show this activity, just we connected these two wires with a battery, and here we have the bulb, and here we have some gaps with having some clips. Okay, in between clips you arrange the different metals. You take one copper wire, other one you take aluminum wire, or you take silver wire. Anywhere you can take, you connect this when you switch on this battery, it will get glow, the bulb get glow. So this activity shows that metals, through the metal wire the electricity is passed, right? Means the metal wire allows the electricity, means they are good conductor of electricity. Set up an electric circuit. Place a metal in the circuit between the terminals A and B. The bulb glows. So what it indicates? It indicates that metals are good conductors of electricity. The wires that carry current have a coating of PVC or a rubber like a metal. They are insulators to prevent from the electric shock. Okay, the wires which are we coated with the PVC wires, whatever we used in the wires in the home, and those wires are coated with the PVC coating. Okay, to prevent from the shocks, and they coated with the PVC insulation. And next one, sonority. When you beat any metal, it creates sound, right? Ringing sound. It creates ringing sound. The ringing sound is called as sonority. And when you beat the wood, can you hear that sound, ringing sound? No, we cannot hear the sound. When you beat any metal, then we can hear the sound, that ringing sound of the metals we called as sonority. It is the ability to produce the sound on striking hot surface. Then metals are sonorous, so they are used to make the bells. Now physical properties in the case of non-metals. Then by looking these non-metals, are they having the shiny nature? No, and they are looking like the dull nature, right? Quite opposite natures to the metals. Now metals are hard in nature and these are the brittle in nature. When you hammer it, then it will convert it into powder, right? Metal do not produce the sound, so it do not have the sonority. Non-metals do not produce the sound, and the non-metals do not have the property of sonority. And non-metals not a good conductor of heat and electricity. And non-metals, now you take hardness and they are brittle. Malleability, we cannot convert into sheets. That when you take any non-metals, when you beat that, we cannot convert it into sheets. Then malleability is not there in the case of non-metals, and ductility also not there. And all non-metals we cannot convert it into thin wires. And conduction of electricity, except graphite, remaining all non-metals are poor conductor of electricity. Sonority means they do not produce the sound. Example for the non-metals we have taken here: graphite, coal, and what is that powder? Sulfur and iodine powder we have taken, right? They are the very few in numbers. Example for non-metals are carbon, sulfur, iodine, oxygen, and hydrogen gas. Non-metals are solids or gases except bromine. Bromine is a liquid. And only very few non-metals have some physical properties of the metal. We move on to the next one. We cannot group elements based on the physical properties alone, as there are many exceptions are there. Okay, by seeing the physical property, we cannot consider all these metals are showing like this property, and some exceptions also there. Okay, by using the physical property, we cannot consider which one is a metal, which one is non-metal. Some exceptions are there. You have to remember that exceptions. What are the exceptions we have here? We cannot group elements based on the physical properties alone, as there are many exceptions. Okay, we cannot group elements based on the physical properties alone, as there are many exceptions. What are the exceptions we have here? Example: metals except mercury or solids at room temperature. Except mercury, remaining all other metals are solid at room temperature. Now you see the mercury at room temperature, which is in the liquid state. Here we can see the liquid state of the mercury, right? Now metals have high melting point, but gallium and cesium have very low melting point. They melt if keep on the palm. When you keep this gallium on the palm, it get melted. By taking the temperature from your hand, it can get melted. Means that gallium and cesium, except gallium and cesium, remaining all other metals are having the high melting points, right? Iodine is a non-metal, but it is a lustrous property. This is iodine crystals. Now these are having the shiny nature. All other non-metals are not having the shiny nature. They are looking dull appearance. So except iodine, the remaining all other non-metals are does not showing the lustrous property. Next one is a carbon is non-metal that can exist in the different forms. Allotropes. Diamond is the hardest natural substance and has very high melting and boiling point. Now you see most of the non-metals are not hard in nature except diamond. So diamond is the hardest substance, right? That is a non-metal also, but it is a hardest substance. Now, and also it is having high melting point and boiling point, and this diamond is also having the high melting point and high boiling point. Alkali metals are so soft and can be cut with a knife. They have the low densities and low melting points. Okay, and by using the knife we can cut these alkalis very easily. Alkalis means the first year group metals we can cut with the knife. That means they are the soft metals. Other metals are hard in nature. Now when you summarize all these here, okay, when you summarize all this, now here we have the physical properties of the metals. Metals are solids except mercury. Except mercury, the remaining all other metals are solid in nature at room temperature. Metals are hard in nature except lithium, potassium, sodium, and these metals we can cut with a knife easily. Metals are malleable. Malleable means we can be beaten into thin sheets. That property we called as the malleability. And metals are ductile, so it can be drawn into thin wires, and that means the 1 gram of gold we can be drawn into how much distance, how much length, that is 2 kilometer length. So that means it indicates the ductility property. Metals have high melting point except gallium and cesium. Gallium and cesium are having the low melting point. When you keep on the palm, it get melted. By taking the temperature from the hand itself, it get melted. The remaining all other metals are having the high melting point. Now you see metals have high boiling points also. Metals are good conductors of heat, and best conductors are silver and copper, and poor conductors are lead and mercury. Metals are good conductors of electricity, and best conductors are silver and copper wire. Okay, in electrical transmissions wire we are using that copper and silver wires. Okay, now metals are sonorous, which produce sound when it beaten. Okay, these are the physical properties of the metals. Now we come to the physical properties of non-metals. Non-metals may be solids, liquids, or gases. Solids are, for example, solid non-metals are carbon, sulfur, phosphorus, and liquid non-metal is bromine, and gaseous non-metals are oxygen, hydrogen, and nitrogen gas, etc. And non-metals are soft except diamond. So diamond, which is the hardest natural substance, right? All other non-metals are soft in nature except diamond. Non-metals do not have the luster, means except iodine crystals, remaining all other non-metals appearance as dull look, means they do not having the shiny nature. Non-metals are not malleable, we cannot drawn into sheets, we cannot beaten into sheets, and non-metals are not ductile, we cannot drawn into the wires. And non-metals which are solids and liquids have low melting points. Non-metals which are solids and liquids have low boiling points. Okay, the non-metals are solids, whatever it is present, the physical state of non-metals, some of the non-metals are exist in the solid state and some other exist in the liquid or gaseous state, and all these non-metals are having the low boiling point and low melting point. Okay, and non-metals are bad conductor of heat, and non-metals are bad conductor of electricity also, and non-metals are not sonorous, right? These are the properties of non-metals. Now we are going to discuss about the chemical properties of the metals. Okay, so in that first one we have that burn magnesium ribbon, collect the ashes and dissolve it water, magnesium hydroxide is formed. What will happen here? When you take the magnesium ribbon, when you burn in the presence of the air, so the magnesium burns with the oxygen, it will convert it into magnesium oxide, white color powder is formed, and that powder when you dissolve in the water, it will give the magnesium hydroxide. Now you see this magnesium, when it is react with the air means you have to take your oxygen, when it is burns with the oxygen, it converted into magnesium oxide. When you dissolve this magnesium oxide powder in water, and it will give the magnesium hydroxide, MgOH taken twice, and this magnesium hydroxide is having the basic in nature. Then how do you test this basic in nature? When you take the red litmus, when you take the red litmus, just you keep it in the magnesium hydroxide solution, then this magnesium hydroxide, what it will do, it will convert the red litmus into blue, and this shows that magnesium hydroxide is having the basic in nature, right? And test this solution with the red and blue litmus. Red litmus becomes blue, so that means here magnesium hydroxide is basic. Okay, all metals burns with the oxygen, they form the metal oxides, and when you dissolve this metal oxide in the water, some of the metal oxides will give the basic in nature. And how do you test this basic in nature? When you take the red litmus and when you keep it in that solution, the red litmus becomes blue, so this indicates that hydroxides of the metals are basic in nature, right? So now here we have the non-metals. You take sulfur. When sulfur burns with the oxygen, it produces the sulfur dioxide gas. When this sulfur dioxide gas passes into the water, it will give the acids, and it will form the acids. That's why we call it as non-metallic oxides are acidic in nature, and metal oxides are basic in nature, right? So burn the sulfur powder, collect the fumes of the sulfur dioxide, placing a test tube over the burning sulfur, add some water into the test tube and shake it, then sulfurous acid is formed. Then how do you test this acid or not? By taking the blue litmus paper. When blue litmus paper turns into red, that means it is acid. right? Now the sulfur burns with the oxygen, it gives the sulfur dioxide gas. When this sulfur dioxide dissolved in the water, then it will form the acid, that is sulfurous acid, right? Now what happens when metal burn in air? Now when you burn the metals in air in presence of oxygen, when you burn the metal, the sodium burns with the yellow golden color. When you burn the magnesium burns with the oxygen, it will form the it will give the white color dazzling flame, that is color is white color dazzling. When you burn the copper, we can see the blue green color here, combination of. When you see the aluminum, we cannot observe the color, but here white color sparklers are coming, right? So when you burn the any metal, so it shows that characteristic color, okay? And that is a flame test, that is we called as a flame test. Try to burn various metals like aluminum, copper, iron, lead, magnesium, zinc and sodium over a flame. Sodium burns easily with yellow flame, that golden yellow color we can observe. So magnesium gives a white color, copper gives a blue green color, and aluminum also gives a white color, right? And the metal surface appears silver white after burning. Now after burning, what will happen? The silver surface we can observe here, right? The reactivity of metals to oxygen is decreasing order is sodium, magnesium, aluminum, zinc, iron, lead, copper. Means sodium is a more reactive element, then magnesium, after that magnesium, after that aluminum. Finally the copper is having the less reactivity. Of the other products, metal oxides are there. Sodium oxide is soluble in the water. Other metal oxides are insoluble in the water. Okay, the metal oxide which are soluble in the water we called as alkalis, right? Sodium oxide we can easily it can easily dissolve in the water, like magnesium oxide also it can easily dissolve in water. Those metal oxides which dissolved in the water, and that metal oxides we called as alkalis, right? Basic in nature. Some of the other metal oxides are insoluble in nature. Now you see, these are the different flame colors. When you burn the lithium, it will give the crimson red color. When you burn the sodium, it will give the golden yellow color. When you burn the potassium, it will give the lilac color. And when you burn the calcium, so it will give the yellow red color. When you burn the barium, it will give the green apple color. And these are the different flame tests of the different metals, right? So now chemical properties of the metals. What happens when metal burn in the air? Now already we discussed in the case of the magnesium, when you burn the magnesium and in presence of oxygen, so it burns with a white color dazzling flame. Afterwards we will get the magnesium oxide powder. When you dissolve the magnesium oxide powder in the water, it will give the magnesium hydroxide, which is in the basic in nature, right? Now almost all metals combine with the oxygen to form the metal oxide. So when metal is burned with the oxygen, so it will form the metal oxide. When copper is heated in the air, it forms copper 2 oxide, like a black oxide we can observe here. Now you see, before heating the copper, which is in the brown color, after heating the copper in presence of the oxygen, so it will form the copper oxide, which is in the black color powder, right? Now similarly, aluminum also, when you heat this aluminum in the presence of oxygen, so you will get Al2O3, that is aluminum oxide, which is in the white color. Okay. Then metals burns with the oxygen, what will happen? It will produce the metal oxides, right? Now what happens when metal burn in air? In this case, metal oxides are basic in nature. Then how do you know that metal oxides are basic in nature? When you dissolve in the water, they give the corresponding hydroxide, they form the corresponding hydroxide. But some metal oxides such as aluminum oxide, zinc oxide shows both acidic and basic properties. Then all metal oxides are shows the basic behavior, but exception is there, aluminum oxide and zinc oxide, and they are showing the both properties, basic property as well as the acidic property. Okay, when this aluminum oxide, when it is react with a base, in that case it behaves as a acidic character. When this aluminum oxide, when it is react with the acid, and it behaves as a basic character, means it can it can shows the both acidic and basic properties. Now you see, this is aluminum oxide. When it is react with the acid HCl, it will give the salt and water. The salt we formed here, AlCl3, aluminum trichloride, and water is formed here. When this aluminum oxide also react with sodium hydroxide, okay, aluminum oxide reacts with the sodium hydroxide and form the sodium aluminate and water. right? This is a part of the sodium aluminate, right? And means aluminum oxide is showing the two properties, acidic property and basic property. How do you know it is showing the acidic property? Acids react with the bases, then form the salt and water. When it is react with the base, it exhibit the acidic behavior, right? Aluminum oxide, when it is react with the acid, it shows the basic behavior, means it is showing the both behaviors, acidic behavior as well as the basic behavior. This aluminum oxide, when it react with the hydrochloric acid, it will form the aluminum trichloride and also water. When aluminum oxide react with the sodium hydroxide, it gives the sodium aluminate plus water. Means this aluminum oxide, it can react with as well as acid and both. That means the oxides, the metal oxides, which is having the both properties, acidic oxide and basic oxide, and acidic behavior and also showing basic behavior, called as the amphoteric. Aluminum oxide we consider as the amphoteric. Okay, and these are the amphoteric oxides, and they react with the both acids and bases to produce the salt and water, and which are called as amphoteric oxides, right? Now move on to the next one. Most metal oxides are water insoluble, but some sodium oxide, potassium oxides are soluble to form the alkalis. Now, here already we discussed all metal oxides do not dissolve in the water, and some of the metal oxides only dissolve in the water. Those metal oxides which are dissolved in the water and form the hydroxide, called as the alkalis. Okay, those metal oxides which are dissolved in the water and form hydroxide, called as alkalis. Now you see, most metal oxides are water insoluble. Okay, but some metal oxides like sodium oxide, potassium oxides, which are soluble in the water and forms also alkalis. Now you see, sodium oxide, when you dissolve in the water, it gives the sodium hydroxide aqueous solution, and potassium oxide, when you dissolve in the water, K2O, when you dissolve in the water, H2O, so it gives the potassium hydroxide aqueous solution. All metals shows different reactivities towards the oxygens. Metals such as the, now is a reactivity, metals shows different reactivities towards the oxygen. Metals such as potassium, sodium react so vigorously and that they can catch the fire if kept in the open, so hence they are kept in the kerosene oil. Okay, now you see, this is a sodium and this is a potassium. We stored the sodium and potassium in oil or kerosene. So when you take it out, then what will happen? It react with the moisture, air, and it catches the fire. So that to prevent that accident, so these sodium and potassium we stored in a kerosene or wax or oil, right? Now move on to the next one. Some metals react with the water to form a metal oxide and hydrogen gas, right? When metals react with the water, for example, you take the sodium lump, just you put it in the water, then what will happen? This metal, when it is react with the water, it forms metal oxide, and also it liberates the hydrogen gas. It liberates the hydrogen gas. Now you see, here we can, when you dissolve the sodium, when you add the sodium in the water, then what will happen? Here we can see the sodium metal catches the fire, right? Now metal, when react with the water, it forms the metal oxide and liberates the hydrogen gas. And this metal oxide, when you dissolve in the water, it gives the metal hydroxides. Now you see, metals like potassium and sodium react violently with the cold water also. Even cold water also, metal like sodium and potassium reacts violently like this, and it catches fire also, and it is an exothermic reaction. During this process, heat is liberated, right? Now you see, that's why this reaction we called as a exothermic reaction, so that the evolved hydrogen catches fire. Okay, when metal react with the water, what happened? It liberates the heat, right? Because of that heat, the hydrogen gas get that heat and it converts as a fire, and it catches the fire, right? Because of this hydrogen gas catches the fire. Now you see, potassium metal we are taking, so we are adding the water, then what will happen here? We got here potassium hydroxide, and it liberates the hydrogen gas, and here it liberates some amount of heat also, right? And also we call it exothermic process. Sodium, when dissolved in the water, then what will happen? It forms the sodium hydroxide aqueous solution and liberate hydrogen gas, and in this process heat also liberated, right? Now when in the case of calcium, so calcium reacts with water less violently. So compared to the sodium, potassium and sodium react water with vigorously and violently, but calcium reacts with the water less violently. The heat evolved is not sufficient for the hydrogen to catch the fire. Okay, whatever the amount of heat is liberated, that is not sufficient to get the fire for hydrogen gas, right? So in this case we cannot see the fire, right, in the case of calcium. Then when calcium reacts with the water, so it will form the calcium hydroxide aqueous solution, and also it liberates the hydrogen gas. Is it clear? Now why this calcium floats on the water, surface of the water? This calcium, when it is react with the water, it liberates hydrogen gas. The liberated hydrogen gas attached with the remaining calcium metal, and due to this the calcium metal float on the water, right? Calcium floats because hydrogen gas bubbles sticks to the metal surface. So in this case, so calcium metal float on the water. Now you see in the case of the magnesium, magnesium only reacts with the hot water. Calcium reacts with the normal water, but compared to the potassium sodium, the reaction is normal, right, less violent. And in the case of the magnesium, magnesium do not react with the cold water and normal water. It can react with only hot water. Magnesium reacts with the hot water, not with cold water. It also floats because hydrogen gas bubbles stick to its surface. When magnesium burns with the water, it forms the magnesium hydroxide and liberates the hydrogen gas. Okay, now move on to the next one. What happens when metal reacts with the water? So when you take the metals like aluminium, iron, zinc, and these aluminium, zinc, iron having the low reactivity, so they do not react with the normal water as well as the hot water. They can react with only steam. They can react with the steam. Steam means it is having the high energy and high pressure and high temperature also, right? So it can react with only steam. Aluminium, iron, zinc react with only steam and not with cold or hot water. So when aluminium react with the water, so it will form the aluminium oxide and it liberates the hydrogen gas. Whereas in the case of, you see, when magnesium and calcium or sodium and potassium, when these metals are react with the water, it will form the corresponding hydroxide. So now you see in the case of the sodium also we are getting the sodium hydroxide, potassium will form the potassium hydroxide, and now this calcium form the calcium hydroxide, magnesium form the magnesium hydroxide, but aluminum is not forming the hydroxide. It is giving only oxides. It is forming only oxide, aluminium oxide only you are getting, and in this case also it liberates the hydrogen gas, right? So iron also when react with the water, which is in the steam form, it can react with the steam only and form the ferric oxide solid, and it liberates the hydrogen gas. Metals such as lead, copper, silver and gold do not react with the water at all. Okay, and the low reactivity, because of the low reactivity nature, this lead, copper, silver and gold, they do not react with the water at all. Means they do not react with the cold, normal water, hot water, and also they do not react with the steam also. Okay, and these aluminium and iron, when it is react with the steam, the gas wool soaked in the water. Now you see here we have one experiment. So in this experiment we have taken one test tube. In the test tube we have kept one glass wool, right? So when you heat this glass wool, the water present in the glass wool converted into steam, and this steam react with the we kept one metal sample like aluminium and iron. When you keep like the metal sample, and this steam can react with this metal, and it can produce the hydrogen gas. When you pass this hydrogen gas into it, so we can form here some air bubbles because of the hydrogen gas liberated into it. So we are passing this hydrogen gas into the soap solution. Okay, so in this way we can perform this activity. Now the reactivity of metals with the water in the decreasing order. Next, sodium, potassium are having the high reactivity, and they react very violently. Calcium only react with the normal water. Magnesium can react only with the hot water, but aluminium, iron can react with the steam only, right? And this is the reactivity order, reactivity of the metals with the water in the decreasing order. Which one is having the more reactivity? Sodium. Next to potassium, calcium, magnesium, aluminium, iron. Aluminium, iron are having the low reactivity with water. For that reason they can react with only steam, not with cold and not with normal water. Okay, now here we have summarize is there. Okay, now the reactivity of different metals with the water is different. Now you see, sodium and potassium react violently with cold water to form sodium hydroxide, and the hydrogen catches the fire. Okay, I have summarized all the points here, right? Calcium reacts less violently with water to form calcium hydroxide and water and does not catch the fire. Magnesium reacts only with the hot water to form the magnesium oxide and liberates the hydrogen gas. Metals like aluminum, iron, zinc react only with the steam to form the metal oxides and hydrogen gas. Metals like lead, copper, silver and gold do not react with the water, right? So in the next slide we have here what happens when metals reacts with the acids, right? When metals reacts with the acids, metal when react with the dilute acid, it will form the salt and it liberates the hydrogen gas. Now you see here, but all metals do not react in the same manner. Only some of the metals only react like this. When metal react with the dilute acid, it will form the salt and it liberates the hydrogen gas. Now, put aluminum, copper, iron, lead, magnesium and zinc separately in test tubes containing the dilute hydrochloric acid. Suspend thermometers in test tubes so that their bulbs are dipped in the acid. The following reactions are occur. Now you see, when magnesium react with the hydrochloric acid, it will form the salt magnesium chloride and it liberates the gas hydrogen. When aluminum reacts with the HCl, it forms the aluminum trichloride AlCl3 salt and it liberates the hydrogen gas. Zinc when it is react with the hydrochloric acid, it forms the zinc chloride ZnCl2 and also it liberate the hydrogen gas. When iron react with the HCl, it form the FeCl2 and also it liberates the hydrogen gas. Okay. Now magnesium shows the fastest reaction and hydrogen bubble formation and records highest temperature and it is the most exothermic temperature. Okay, we placed in all test tube like the thermometers, right, which shows the more temperature, that magnesium. The reactivity decreases in the order. So magnesium reacts more compared to the aluminum, zinc like iron. Right, copper does not react with the dilute HCl, so bubbles are not formed and no change in the temperature. When you place the copper in the HCl, we cannot observe the bubbles. Hydrogen gas bubbles is not evolved in the case of the copper, and that means the copper do not react with the acids. Right, now hydrogen gas is not evolved when a metal reacts with the nitric acid. Now see, in case of hydrochloric acid, we can observe the liberation of the hydrogen gas. But in the case of when you take this same reaction with the nitric acid formula is HNO3, right? When this react with the HNO3 as a strong oxidizing agent, it oxidizes the hydrogen and it will convert it into water. Right? Are you getting my point? What is happening here? So, for example, you take the magnesium when react with the HNO3. In case of HCl, you will get the magnesium chloride and it liberates the hydrogen gas. But in case of nitric acids, you will get MgNO3 taken twice. Okay, and in this case we are not getting the hydrogen gas, but in this case we are getting only water, right? Then the liberated hydrogen gas, then it reacts with the HNO3 as a strong oxidizing agent and it oxidizes to hydrogen to water molecule. Okay, in this case we are not getting the hydrogen gas, right? When the reaction is carried out by the HNO3, in that case we are not getting the hydrogen gas. So we are getting water molecules we are getting, and the liberated hydrogen gas and react with the HNO3 and it formed into water. Right, now you see, hydrogen gas is not evolved when a metal reacts with the nitric acid. It is because HNO3 is a strong oxidizing agent. It oxidizes the hydrogen to the water and itself gets reduced to nitrogen oxide like N2O, NO or NO2. But magnesium and manganese react with very dilute HNO3, evolving the hydrogen gas. Now this magnesium, when it is react with the very dilute nitric acid, very dilute means you have to add more water into it, then it will become very dilute. So when it is react with a very dilute acid, the magnesium also gives hydrogen gas. In that case magnesium gives the hydrogen gas when it is react with the very dilute nitric acid. Magnesium or manganese, both metals can give the hydrogen gas when it is react with very dilute nitric acid. Is it clear? Now move on to the next. Okay, now this gold and copper and silver, they do not react with the acid HCl and HNO3, but they react with the aqua regia. Aqua regia means when you take the HCl 3 ml and HNO3 1 ml, when you combine these two, then it will form the aqua regia. Okay, the 3:1 ratio of HCl and HNO3 is called as aqua regia. So when you dissolve when you keep the biscuit in the aqua regia. Now you see the slowly the solution turns, the color of the solution turns into golden yellow. That means what it will indicate, the gold is dissolving in aqua regia. But they do not react with the HCl single and HNO3 single. When HCl and HNO3 mix in the 3:1 ratio, in that solution when you put the gold or gold coins or gold biscuit, then what happens here? This gold dissolves and form like this solution. Means gold react with the aqua regia. It is highly corrosive fuming liquid. It is one of the few reagents that can dissolve the gold and platinum. This gold and platinum can dissolve in the aqua regia. Now, how do metals react with the solution of the other metal salts? Okay. So I have performed one activity also. So please go to my videos shorts. You just search for the displacement reaction of the copper sulfate solution and iron. And I have made one video. So I will keep in the group description also, YouTube description. And please go and watch that video before coming to you. Then how do metals react with the solution and other metal salts? And also, all of you, please, I am requesting you, please download the chapter notes from group description. I am providing the link in the group description, and you can download the notes from there. Okay. Now you see, how do metals react with the solutions of other metal salts? Now in this case, what we are doing here, put a clean copper wire in iron sulfate solution and iron nail in the copper sulfate solution taken in the test tubes. So here we are doing the same thing here. First we are taking the copper sulfate solution. Into that we are keeping the iron nail. Okay. Then you are just reversing. Similarly, you take the copper tubes or copper wires and place it in the iron sulfate solution. In the both cases, what do you observe? Let us see now. After 20 minutes, blue copper sulfate solution turns into green. Now, copper sulfate solution, when you keep the iron nail in the copper sulfate solution, what happens here? The blue color of the copper solution slowly it changes into the green color. Green color, it turns into green color. Why that green color is forming here? So iron is more reactive than copper, so it displaces copper from the copper sulfate to form the iron sulfate. So copper sulfate solution turns green. Now you see, this is the iron, right? When it is react with the copper sulfate, this copper is displaced by the iron and form the iron sulfate aqueous solution. This iron sulfate appears in the green color and the copper is separated here, right? And this is a displacement reaction. That is, the reactivity metals displace less reactive metals from their compounds in the solution or molten form, right? And this is example for the displacement reaction. The high reactive metal like iron can displace the copper from its compound, that is copper sulfate, that is having the low reactivity. Iron is having the high reactivity. The high reactivity metal can displace the low reactive metal from its compound. It means here iron is displacing the copper sulfate from the copper. Now you see, in the place of copper the iron is coming. Okay, then we get here iron sulfate. The copper is separated here. Okay, that means that the most reactive element iron can displace the low reactive element of copper from its compound copper sulfate solution. Okay, and this type of reactions we called as a displacement reaction. Now you see, displacement reactions are the best evidence for the reactivity of the metals, right? Now here we can see this is a copper sulfate which are in the blue in color. So after some words, what will happen? The color of the solution turns to green, right? Because of the formation of iron sulfate, the copper is deposited on the iron nail. Okay, whatever the separated copper atom, which is deposited copper metal atom, which is deposited on the iron nail, right? Now if a metal A displaces metal B from its solution, it is a more reactive than the B. Now you see, this is a is having the more reactivity, it displaces the B from its compound, so it is forming the AC plus B, right? All metals do not react with reagents like oxygen, water and acids, so we cannot put all the metal samples in the decreasing order of their reactivity. Now in the case of reactivity series, I will give one code to remember this, right? So you remember reactivity series in this way: पोसो का मा जिल H chop, right? पोसो का मा जिल H chop. Chop means platinum or H chop. Platinum will come here, so they have not given here platinum, but it is not required also. Okay, this is a platinum. So how do you remember this? Potassium, sodium, calcium, magnesium, aluminium, and up to here, yeah, पोसो का मा जिल, Jil means zinc, iron, Jil. Jil means posokama Jil. Zinc, iron, lead. Right? H. H. Chop. CHAPA. H chopper. Okay. Then you have to remember like this. Posokama Jil H chopper. Posokama Jil H chopper. Po means potassium. So means sodium. Ka means calcium. Ma means magnesium. A means aluminium. Jil zinc, iron, lead. H hydrogen. Chapa copper, hydrogen, and what is that? Silver and platinum. Next gold will come. Are you able to see this? Right. Posokama Jil H chapa. And here posokama up to here, these are high reactivity metal. Most reactive metals. These are the most reactive metals, and these are having the moderate reactivity. Okay, and these are having the less reactivity, right? So the reactivity order decreases from potassium to gold. Okay, and which metals are having the more reactivity? Potassium, sodium, calcium, magnesium, aluminum. Up to here, and these metals are showing the high reactivity order. When you come to zinc and iron, lead, what will happen in this case? The reactivity of these metals slightly decreases, and this copper, mercury, silver, platinum, gold, these are the valuable metals, and valuable metals do not react with do not react means these are having the less reactivity. Okay, valuable metals are having the less reactivity. Now you come to here, how do metals and non-metals react with each other? Okay, when you combine the metal with the non-metal, they can react each other and form the metal compounds, metal ionic compounds. We can see here metal ionic compounds it can form, right? Now you see every metal atom trying to get a noble gas configuration. For example, when you take the sodium here, okay, sodium in first orbit it consists 2 electrons, and second orbit it consists 8 electrons, and third orbit it consists only 1 electron. Okay. To get the octet electron configuration, so it has to lose its electron, right? So what it will do? So it loses 1 electron and form the Na plus ion. Okay, now you see Na plus ion we are getting after losing 1 electron. Now it will get the octet configuration. Every atom trying to get the nearest noble gas configuration or octet configuration or full-filled configuration, or we can call it a stable configuration, right? When sodium lose the electron, it will form the Na plus. This is having the 2-8 configuration, 2-8 electron configuration, right? And here we are getting only Na plus now. Now in the case of non-metal, you take the chlorine, right? Then chlorine, you write the electron configuration of the chlorine, and sodium atomic number is 11 and chlorine atomic number is 17. Just these 17 electron you distribute in the different orbits. First orbit consists 2 electrons, and second orbit consists 8 electrons, and third orbit consists 7 electrons, right? So to get the valence electron configuration, or to get the octet configuration or stable configuration, it require 1 electron. So after taking 1 electron, what will happen? The Cl, after taking 1 electron, it will form Cl minus. After taking 1 electron, so it will get the stable configuration, that is 8 electron configuration in the last shell. Okay, every atom trying to get the 8 electron configuration in its last shell. Okay, that is a stable configuration. Now because of this, the sodium after losing 1 electron, it form Na plus ion, and then chlorine after gaining the electron, it form the Cl minus ion, and these two ions combined each other and form the ionic compound, that is we called as NaCl. NaCl will form, and this NaCl is a ionic compound. Because of strong electrostatic attraction forces, because of this plus charge and minus charge, unlike charges get attract each other, because of this strong attraction force, this ionic compound is formed here, that is we called as NaCl, right? So here we can form the NaCl. Here we can see the NaCl ionic compound. Okay, now you see a sodium atom has a 1 electron in the outermost shell. If it loses the electron from the last shell, that M cell, then its L shell becomes the outermost shell, giving a stable octet. Now you see, this is the K shell, right? And this is the L shell, this is the M shell. When you remove one electron from the M shell, then it will get the L shell configuration, that is the 8 electron configuration. This is the stable configuration. After losing electron, it converted into sodium plus ion. Now the number of electron is 10, but the nucleus has 11 protons, so there is a net positive charge giving a sodium cation. Okay, because of after losing electron, now it will get the positive charge. Then how it will get the positive charge? Then sodium is, already you know that sodium is having the 11 electrons, right? So the sodium is having 11 protons and 11 electrons. Is it clear? Sodium atomic number is 11, right? So it will consist 11 electrons, 11 protons. Protons are having the positive charge and the electrons are having the negative charge. After removing one electron from this, we remove one electron, this will become 10 electrons and the protons remain same, right? So 11 positive charges are there, 10 negative charges is there. The net effect is 11 minus 10 is 1 positive charge is left over because of one proton is excess is here. So due to this, the sodium will get the positive charge. Is it clear everyone? Why this sodium is getting the positive charge, right? Now chlorine has 7 electrons in its outermost shell, that is M shell. Now you see K, L, M. In the M shell we have only 7 electrons in the case of the chlorine. So to get the 8 electron configuration, so the chlorine gain 1 electron from the sodium and it will form the Cl minus and the last orbit configuration. Now you see it is a 8 electron configuration, stable configuration. Okay, so now here chlorine has 7 electrons in outermost shell and needs one more electron to complete its octet. So for that reasons, when sodium reacts with the chlorine, the electron lost by sodium is taken up by the chlorine. Thus chlorine gets a stable octet and total 18 electrons configuration in Kl and M cell, but its nucleus has only 17 protons, more than the chlorine atom gets a unit negative charge. So in this case what happens here? Then what is the atomic number of the chlorine? That is 17, right? So means it is having 17 electrons and 17 protons. Okay, after taking one electron from the sodium, that electron number increases to 18 and the proton numbers remains same. Means here 18 negative charges are there, 17 positive charges are there. 18 negative charges are there, 17 positive charges are there. So minus 18 plus 7, how much it is? Minus 1. 1 electron, because of 1 electron is excess. The 17 electrons are neutralized by 17 protons, but 1 electron is excess is there. Because of that electron, and this chlorine is getting negative charge. Okay, is it clear? Now you see, thus so the chlorine atom gets a unit negative charge forming a chloride ion. Thus sodium and chlorine have give and take relation. So it will give one electron and it forms the sodium plus ion, and chlorine takes that electron and forms Cl minus ion. Because of an oppositely charged, sodium and chloride ions are held by strong electrostatic forces of attraction to exit as sodium chloride, NaCl. This NaCl does not exist as a molecule but aggregate of oppositely charged ions, right? And like this, this formation of the sodium chloride takes place, right? The sodium will get the positive charge and chlorine will get the negative charge. Because of the oppositely charged, what happens? And here NaCl ionic compound is formed, right? Now move on to the magnesium chloride. In the case of magnesium also we can assume similarly. So magnesium atomic number is 12, right? Magnesium atomic number is 12. In the first orbit, the K shell, it is having the 2 electrons, and in the L shell it is having the 8 electrons. In the M shell it is having the 2 electrons. Okay, to get the 8 electron configuration, it has 2 electrons excess. Okay, after removal of these 2 electron, what will happen? This magnesium takes positive 2 plus charge, and after taking 2 electrons from it, then now you see the electron configuration, 2-8 configuration it will get, right? Similarly, chlorine, already we discussed this chlorine is having 287 configuration, and to take this electron, this Cl will become Cl minus. Here we have the 2 electrons. Okay, one chlorine will take one electron only. For two electrons, two chlorines are required. This two chlorine takes two electrons and form 2Cl minus. Because of these charged ions, magnesium 2 plus and 2Cl minus, because of this oppositely charged, they get the strong electrostatic attraction forces and form the MgCl2, magnesium chloride ionic compound. So in this way we get the magnesium chloride ionic compound, right? Now you see, magnesium after removal of 2 electron, it will form magnesium 2 plus ion, and chlorine after absorbing electron, so it will form the Cl minus ion, right? So after this, the compounds formed by the transfer of electrons from a metal to non-metal are called a ionic compound and electrovalent compound. Then how do you define this ionic compound? The transfer of electrons takes place from where to where? Metal to non-metal. In the case of sodium, sodium giving its electron to the chlorine, then electron transfer takes place from the sodium to chlorine. And in the case of the magnesium, magnesium giving two electrons to two chlorine atoms, here electrons transfers takes place from the magnesium metal to chlorine non-metal. Okay, in this way we are getting the ionic compound. The compounds formed by the transfer of electrons from a metal to a non-metal are called ionic compounds, or also we called as electrovalent compounds. So yeah, if you like this video, please share, like, subscribe and comment, and to continue this and watch the part 2 also. Have a nice day. Bye.